Hello, I'm Xu from Chinese Academy of Sciences. Today, I'm going to introduce our research work, Cooper, testing the binding code of scripting languages with cooperative mutation. It's a joint work with researchers from Qianxin and Penn State University. As we all know, scripting languages is very useful and powerful. It's very easy to learn and develop. Nowadays, scripting languages are integrated into document processing programs. For example, JavaScript is integrated into PDF and HTML. VBA code is integrated into Office document. In these programs, embedded script code are usually used to manipulate the content elements of a document. Vulnerabilities in these embedded scripting languages are very dangerous. Attacks can exploit vulnerabilities in these programs to execute abuse code and take control of the system. And every year, many vulnerabilities are discovered in embedded scripting system. So it's essential for us to design an effective method to find bugs in embedded script code. First of all, I'm going to introduce the structure of document with embedded script code. This kind of document usually consists of two parts, native objects and script code. Native objects make up the main content of the document, such as pictures, annotations, paragraphs, input box, and tables. Script code is an interpreted language embedded in a document, usually used to automate the manipulation of content elements. When application opens a document, it first passes the native objects and then interpret and execute the script code. To bridge the gap between native objects and the script engine, usually there is a binding layer used to transfer data and transform representation. Secondly, the interaction between native objects and script code often introduces bugs. Specifically, script engine and application are often developed independently, and applications are usually developed in low-level languages, such as C and C++. So there is a gap between high-level scripting language and low-level application. In order to bridge the gap between two sets, a binding layer is usually used to transfer data and transform representation. In this process, vulnerabilities are often caused by inconsistencies between native objects and script code. However, previous work haven't been able to effectively find such vulnerabilities, mainly because they only mutate script code without any mutation in native objects. We take a vulnerability discovered by Cooper to demonstrate our concept. It's Heap overflow in Adobe Acrobat. Successfully exploiting this vulnerability can achieve remote code execution. It's so severe that we were awarded with $2,500 bounty for this particular vulnerability, and it had been patched by Adobe before paper submission. Then let's see how to trigger this vulnerability. First of all, in native objects, we must insert one extra element in the final service as well. Then in script code, we must utilize JavaScript code to change the zoom type of the document to RefW. So as you can see, to trigger this vulnerability, we must mutate both native objects and script code. And traditional one-dimension mutation further cannot find this sort of vulnerability. Inspired by this vulnerability, we want to design a new solution to discover this sort of vulnerabilities related to both native objects and script code. Our solution is cooperative mutation. It's very straightforward. We mutate both native objects and script code in cooperative manner. So we come to the problem, how to achieve cooperative mutation. First of all, we need to infer the relationship between native objects and script code. And then we use the infer relationship to get a mutation in both sides. Specifically, if a scripting API has a potential connection with some objects in a document, we will assign these objects a high priority for mutation. Otherwise, we just randomly choose some objects for mutation. Well, our method is straightforward. There are several challenges to be solved. The first challenge is how to infer the relationship between native objects and script code. Once we have the relationship, we need to solve the second challenge, how to use the inference relationship to get a mutation. However, when we solve these two challenges, we encounter a new problem. There are so many native objects. That means we will have a huge search space for inference relationship and getting mutation is not doable. To solve this problem, we need to reduce the search space. So how to reduce the search space? We plan to categorize all native objects into different categories according to their semantic feature. So let's come to our challenge zero. How to cluster native objects into semantic similar classes. Then this figure presents an overview of our solution. It has three components. The first component is object clustering. It clusters a large number of native objects into small number of object classes according to their semantic feature. Once we have the object classes, we need to infer the relationship between object classes and scripting API. This is the purpose of our second component, relationship inference. This component utilizes a statistical method to infer the relationship. Finally, we come to the third component, relationship get mutation. In this component, we use the inference relationship to get mutation. Then I will show all components in detail. The first part of our solution is object clustering. An object usually consists of some objects, some attributes. Each attribute is a pair of name and object. Through our observation, the name of object usually carries some semantic information. So in the first step, we just class the native objects with their names. It's very simple. We just put objects with different lead name in different categories. However, in some core cases, clustering objects by their name may not be correct. For example, there are some universal names such as kids, parents. To get a fine-grained object classes, we split and merge object classes with the attribute similarity. Specifically, we use that formula to calculate the similarity between native object classes. If the similarity is less than the threshold value, we split a big class into several small ones. If the similarity is greater than the threshold value, we merge these small classes into a bigger one. So in these two steps, we finally get a set of fine-grained object classes. The second part of our solution is relationship inference. We take two steps to infer the relationship. In the first step, we do execution logging for all samples and divide them into two sets. Success set and failure set. Specifically, we prepare a testing code and insert the testing code into the original sample. Then we use the application to open a new sample. If the testing code successfully finds the related elements, we put the original sample into success set. Otherwise, if the testing code cannot find the related elements or produce error, we'll put the original sample into failure set. So through this first step, we have divided all samples into success set and failure set. After we divide all samples into success set and failure set, we use a statistical method to infer the relationship between object classes and scripting API, and we get a relation map. As you can see from the map, the success rate is the percentage of samples that contain this class of objects in the success set. The failure rate is the same percentage in failure set, and the difference is the difference between success rate and failure rate. We think the different value represent the strength of the relationship between object classes and scripting API. In the second part of our solution, we have got the relation map between object classes and scripting API. In this part, we will utilize the relation map to get a mutation. First of all, we determine a target API group. Then we take a traditional method to generate a script code. For native objects, we get a seed sample and select objects in the sample for mutation. Specifically, we refer to the relation map and design algorithm to calculate the mutation probability for each object in the seed sample. In general, the mutation probability is positively correlated with the strength of the relationship. Then we select some objects with mutation probability and mutate selected objects in three mutation strategies. Finally, we synthesize the mutated samples and scripts code together and produce a final input. So let's walk over our solution. For implementation, we developed the Cooper in 4,300 lines of Python code. And Cooper has utilized some open source library. In particular, it utilizes JavaScript, it utilizes PDF to Python library to pass PDF format. It uses zip file and XML Python library to pass word format. For scripts generation, we utilize Domato and improve it with block level template. Cooper currently supports two formats, PDF and Word. It's notable that Cooper is extensible and portable. We can easily add some new features to Cooper and also can apply Cooper to other document formats with limited manual efforts. Then I'm going to talk about Cooper's evaluation. We apply Cooper to real-world programs to find bugs. And we compare the capabilities of bug finding and edge finding in different configurations and tools. We will apply Cooper to three real-world programs, Adobe Acrobat, FoxRadar, and Microsoft Word. In 4 months, we totally found 134 previous unload bugs, got 33 CV numbers, and 59 bugs have been fixed. We were totally awarded with $22,000 bounty. All these vulnerabilities are related to 90 API in 11 objects. We applied different configurations on Adobe Acrobat and recorded the bug finding history in 1 week. As we can see from this figure, Cooper 4 found 18 bugs in 1 week, which is the most among all configurations. This result proves our concept that cooperative mutation is essential to find bugs in binding code. We also do the experiments on FoxRadar. The result is similar to Adobe Acrobat. Cooper 4 always found the most bugs. To test the edge finding ability, we apply all configurations to Adobe Acrobat and record their edge finding history in 1 week. We record both native objects coverage and script coverage. As you can see from these two figures, Cooper 4 can find the most in both types of coverage. We also do the edge finding experiments on FoxRadar and Microsoft Word. Their results is very similar to Adobe Acrobat. Cooper 4 always found the most coverage. These results can also be a proof of our concept. In conclusion, we propose cooperative mutation to testing binding code of scripting languages. Our system, Cooper, found 134 bugs in Adobe Acrobat, FoxRadar, and Microsoft Word. We received 33 CV numbers and $22,000 bounty. And Cooper is now open sourced at this website. Thanks for listening. I'm ready for questions.